Okay, so first of all, I was very happy to learn that some of you are really thinking about these exercises, and coming back to me, you know, it's that's what learning, what a summer school is about. So here is one more exercise. This will, I mean, this is a little bit more complicated, and it's one that I regularly give when as a course on convex integration. It's a simple toy model. This is a toy example. And let me say, okay, so of course, these exercises are some things that, of course, you can Google. If you're very good in searching, you can find them. But not, okay, still good to think about it. And this one has, so there's several solutions. There's one that you can find, there's other ones also. So it's a kind of very simple 1D toy model for convex integration. So what this is about, I mean, this convex integration is a way to construct solutions of nonlinear equations by an iterative scheme. And the one linear equation here is going to be that we are searching for a function on the interval 0, 1. And the nonlinearity is that we want the modulus to be equal to 1. Okay? So it's very simple. No derivatives. Now, and convex integration is an iterative technique. So there's a sequence. Okay, so there's a sequence, Q1, 2, 3, and so on. And we're going to start with 0. U0 is, say, 0, or more generally, something with modulus strictly less than 1 in the whole interval. And we obtain Q plus 1, UQ plus 1, from UQ by adding a high-frequency perturbation. That's what you see in all schemes, the ones that Hyunju presented. I'm only referring to this. Camilo's lectures will be much more detailed about this procedure. And here what we want is something that gets us closer to modulus 1. So, and there's something very explicit you can do. Of course, it's not a unique choice. The problem is very simple. You take the modulus squared at any point x. This is, roughly speaking, proportional to the distance of getting to the constraint. I want to get to 1, so this is non-zero, precisely if I haven't reached the solution yet. And multiply it by 1/2, and add the high frequency term. So this could be something like lambda qx, sine of lambda qx. So it's a periodic function, and you see the structure is I have slow and fast. So the structure is the same, and there's one thing which I think Camilo will talk about extensively, is the concept of subsolution, that this 1/2 times this is supposed to achieve that the modulus of, so if UQ has modulus strictly less than 1, then UQ plus 1 also has modulus strictly less than 1. So there's one simple fact that one can check, that if this is strictly less than 1 for all x, then also UQ plus 1. Okay, that's a simple fact. That's for this 1/2. And then let's say part one of the exercise is to show the following, that we can choose, so it is possible to choose this sequence going to infinity sufficiently fast so that we achieve that the modulus converges to 1 almost everywhere, and the sequence converges, the sequence converges strongly, let's say in L1, to a function of modulus 1. Okay, so this is then our solution. Okay. This is when when we don't care how fast. The faster this convergence is, the easier it will be to prove this. And now comes the difficult part of the exercise, is to fix this to be a power of 2 and show that in fact the convergence rate is also exponential. So 1 minus modulus of u q squared on the 0, 1 is bounded by some constant times 2 to the minus some gamma times q for some gamma. Okay, so that's the more tricky part of the exercise. And I'm happy to discuss, as I said. I'm here for at least until Wednesday next week. Okay, right, so now coming back to the topic of my lectures. So just to recall maybe the basic, let's see, yeah? Yes. Yes, for part 1, you could say that you have this sequence lambdas depending on u0, if you want. That makes things simpler. But as you see in the second part, I'm not... in the iteration scheme, there is no dependence on u. No dependence on what? On the function u0. u0 is the first one. So if q is 0, then this is u1, the formula for u1. It involves u0. u2 has u1, and so on. I'm starting with a given function u0. And the scheme is independent of u0. Given, yes. We are starting with given u0. And u is not... No. U is what this should converge to. U is the limit. Sorry, this is the, let's say, this is the yeah, maybe I think what this is confusing you. So I'm trying to solve this nonlinear equation, okay, by convex integration. So that's the nonlinear equation I want to solve, and this is how I solve it. Okay. Yeah. Yes. Would that depend on the growth of well, okay, so C0, you can't really hope for C0, right? Because the limit is plus or minus 1, almost everywhere, right? So the limit is not going to be continuous. But in a sense, you're right that if I have this decay rate for the L1 norm of this difference, this is sort of the frequency. So just to make the connection to what Ujjwal was talking about, you could say this is like A of x, and this is the W lambda x. So you have some amplitude times some building block. Okay, and so what this statement will say or says, roughly speaking, and you can try to make this rigorous, but it's not that much the point to make it rigorous. But it says basically the amplitude, at least in L1 norm, decays like a power of 2, and the frequency grows like a power of 2. So it gives you some sort of fractional regularity. If these were C0 norms, this would give you C alpha. Here it doesn't give you C alpha because I'm only measuring in L1, but it's the same idea. Okay, good. Any more questions on the exercise? I'll be checking next week for answers. Okay, so now coming back to the setting of my lectures, I have a velocity field, u, which is the limit of these approximations, uq. So this is back to anomalous dissipation and Euler, and these ones are constructed by something like this. Okay, maybe I keep just like this, but of course this one has a lambda q plus 1, and where there is a step that I just briefly mentioned. I'm not sure anyone after me will talk about this, but there is a gluing step. We have to replace uq by uq bar, which is on small intervals a solution of the Euler equations. And then we add this high frequency perturbation, which has the form of the Mikado flow, but it's also composed with the Lagrangian map. So I'm not writing xt lambda x, but because it would be closer to writing like xt lambda q plus 1 of phi of xt. But even this is not correct because this is only true on small intervals, and if you parameterize the intervals by I, you have to sum over I, and the whole formula gets very messy. Okay. So I'm just writing this for now. And so there is this iteration scheme, and for each q, I'm looking at the scalar advection diffusion equation. Where, okay, and there are certain scales. So there is for instance, the amplitude of the perturbation is like delta q. Like in Hyunju's talk, the frequency, so let's say the gradient of the perturbation gets an extra lambda q, and this will correspond to a kappa q, which I briefly explained last time, which is like a negative power of the lambda q. And this one is given rather explicitly. Okay. Okay, maybe I don't say what it is now. It's something determined, okay, from the way these are related, and the main relation here is that this is essentially lambda q to the minus beta, and okay. I'm not really discussing how to make sure that this uq converges to a solution of the Euler equation. That will be the topic, I guess, of Camilo's lectures. And Hyunju was talking about this. I'm just saying, okay, there is this sort of structure for this vector field U, and I want to use that to analyze this equation. Now, the homogenization part in the last lectures gave me that I can hope up to some, there were like 5 or 6 steps, but the main homogenization step gave me an expansion of this rho q plus 1 in terms of rho q plus perturbation, which has this type. And so far I was ignoring the drift, so this is also not really correct. So we need to add, again, this capital phi, the same way I just mentioned it and I erased it, sort of the things that we don't want to talk about. And this chi was essentially, in the computations that we saw, this is a solution of the cell problem. Okay, it was something like this. Now I'm not putting the delta, so this is already the delta, sorry, there's still a lambda. There's still a lambda, but there is no delta 1/2. It's part of the definition of the Q. This is Q. Sorry, it's Q plus 1. Okay, so this is the cell problem. And the next thing I want to explain is how to solve the cell problem. So far, I was just telling you that just by looking at the size of this, and then I have a Laplacian here, I can guess what should be the size of this chi. And the maximum principle is maybe possible to use. The Moser maximum principle would work, but certainly I cannot hope to just use the PDE to get bounds on the derivative of chi, because then this drift starts to enter. And in order to deal with this issue, we actually just write down the solution. The solution is explicit in our case. It's also explicit in the Armstrong-Vicol case. There it's just a single shear. Here it's a Mikado flow. So, okay, the structure of the W is that it's a sum, finite sum over some vectors of some amplitudes times a function. Okay, maybe I can put the psi, the fast variable, function supported on a small tube in the direction of k, where of course we want k dot gradient phi k to be 0. So that's the divergence-free condition. And in fact, okay, it also has to be compactly supported in the orthogonal directions to k. So these are these so the support is like this essentially, and periodic. So it's inside a periodic box. There's many copies of the same tube. Okay. This is what the support of this phi k should look like. And it's actually also in order to be able to write down the vector potential, which I will need to rewrite that as a parabolic equation. It's helpful to actually write phi k as the Laplacian of something else, psi k, where psi k should have the same properties. So also with psi k compact support, I mean compact in the tube, support in the pipe, the same way, and also the orthogonality. Okay, So this is useful because then I can write the vector potential by something like this. Is it somewhere? K. Cross product with the gradient. Okay, so this is just vector potential means if I take the curl of this, that will give me another cross product with K, and then you use the double cross product formula and you get this one. Maybe I should assume here that they are unit length. They are unit length, these vectors. Okay. So, and then there is the normalization, which will give me some sizes of how much, in order to, the L2 norms to make sure these pipes are good. So first of all, I want, this is average over the full periodic cube. I want these to have unit length, and I also want the gradients of the psi to have be normalized. And it's easy to check that by playing with the radii of these tubes and the amplitudes, you can achieve both at the same time. And this is useful for two things. Well, okay, for several things, but the main point is that the cell problem over there, and now I'm forgetting all the subscripts Q, but the cell problem will have the explicit solution, which is 1 over kappa, lambda, and then the sum ak psi k times k. Recall this is a vector, so each component should, okay, so this is, let me write it again here. So this is, if I evaluate this, for the same reason that the Mikado flows, there's no cross-term interaction, this is 0. Okay, this was, if you recall from yesterday's discussion, this is the main culprit. This is the dangerous term. If this is not 0, it will destroy any hope of good estimates. Here it's exactly 0. And then kappa times the Laplacian, well, this is how it's defined. It's just a W. So the lambda, what happened to the lambda? There was a lambda over there. Yeah. So it's super simple. And this means that whenever I'm interested in, slow derivatives of this chi, I can expect the same kind of formulas and estimates that in convex integration that we have. The slow derivatives and the fast derivatives decouple. It has this product structure. That's important. Okay, and now, so then this is explicit. You can also get the homogenized coefficient explicitly, where this is just going to be 1 over lambda times the average of the W J kappa times the average of Wj chi I. So this, okay, this kappa times the identity plus this. Okay, and now this is just kappa times identity plus kappa times, well, that wj chi I. Again, you don't have cross terms. I has to equal j, otherwise you're in a different tube and they are disjoint. So it's just a sum over k, not k and k prime, of ak squared, and then it's the Laplace, so it's psi times phi, okay, which is the same as, maybe there was a minus in the formula, because there should be another minus coming from integrating by parts. So it's going to be this. And k, so it's k tensor k. And this is 1. And then you just realize that this is precisely the same formula that you already saw in Hyunju's first lecture, how to recover the Reynolds stress. It's going to be something that's identity up to scaling plus something small, okay? So the first order term, it will be just a perturbation of the identity. And I think I have lost the lambda, sorry. Okay, the kappa cancels with this kappa, and there's a 1 over lambda. That's one thing. And so I can think of this, okay, and this was the size delta, okay, by my new scaling. So this is, overall, it gives me something like kappa identity up to smaller order terms, plus I think I lost some of these other factors along the way. There must have been another 1 over kappa, maybe, yeah. There's no lambda in that. This is psi.
But then in the second one, there it should be 1 over lambda.
Here also not, because this is without the lambda, but there's some other coefficient here, which now I forgot. You're worried that there is a lambda coming up here?
Yeah, exactly.
No, because this is the homogenization. So this is coming from the cell problem. It has not. There's no explicit lambda dependence in the cell problem. It's because it's psi. I mean, in the sense that it's psi. It's not lambda x. There is explicit lambda dependence only in the. Maybe I should have been lambda 1 over lambda here also. In the amplitude, because of the other scaling with respect to the usual parabolic homogenization, but not in the variables. But let me see. So how did I lose this? Without flow map. Yeah, I'm sorry. I lost this. There should be a 1 over kappa here, which I lost. So the result should be 1 over lambda kappa, and well, there's delta coming from this a squared. In fact, lambda squared. I think there's another lambda somewhere. But the lambdas only come from the maybe there was this 1 over lambda, so I should put a lambda here. Okay, I think this is just fudging. My main point was that it's the identity. I already showed you yesterday how to get the correct size. What I'm showing you here is how to get the correct matrix form, the identity, plus small terms, okay, by the explicit formula of the chi, okay? So now the exercise from yesterday, the linear algebra exercise from yesterday is used when we add the flow map. When we add the flow map, basically the W will have the form, even without this time cutoff functions. So let's say the next level of complexity, it will be like this. So there's the phi. Now it's composed with this flow map, inverse flow map. And in order to keep it divergence free, I have to multiply by the inverse of the Jacobian matrix. And because it's not divergence free, there is a corrector. The corresponding vector potential, which already will include the corrector, is something now I can write explicitly. It's the something like this, k cross gradient psi, again composed with lambda phi, and then again, that's it. Okay, and then to write the drift term inside the Laplacian, inside the divergence, the form will be something like this. So kappa identity remains. There's a 1 over lambda now, because now I am doubling variables. It will be 1 over lambda times ak. And now you use this formula. You have to come up with an antisymmetric matrix, which gives you, multiplying by that matrix gives you multiplication by the vector multiplication. And this one will be this type. So if, let's call this UK, if HK would be corresponding matrix corresponding to multiplying by this UK, then the new matrix has to be this sort of modulation. -1 minus transpose. Okay. Just to say where these formulas come up. Good. So these are just some of the details to fill in order to be able to compare the equation Q plus 1 to the equation Q. Okay, and now having, or after all these details, the statement one obtains is the following. So this is sort of the iterative proposition. Comparing, let's say, comparing rho Q to rho Q plus 1. Equation of rho Q is there. Equation for rho Q plus 1 is the same with Q plus 1. And so there's some notation, because at the end of the day, what we want is to have a lower bound on the dissipation rate. And so let's call this dq. That's just a notation. Okay, so it depends on the time you take, but otherwise it's given by this. Okay, so that's the amount of L2 norm squared that has decreased in time t in the advection diffusion equation. And so then the statement is that for all initial data, which is L2 with average 0. And such that the HS norm, as HN norm of the initial data, let's say homogeneous HN norm, is bounded by some fixed constant times lambda q to the n times the minimum of the square roots of the dissipations of q and q plus 1. Then these are almost the same. So dq plus 1 minus dq is bounded again by some constant, lambda q to the minus gamma times dq. So ignoring this one for a moment, this is the type of estimates we are looking for. Okay, I said this already yesterday, that let's say if you start with q equals 0, this is some fixed, corresponds to some fixed kappa 0. So the fixed kappa 0 gives you, just by applying the Poincaré inequality, gives you some dissipation rate. And then, so let's say d0 is something quite big. Then if I can satisfy this extra condition, then the other ones will be close to the d0, okay? Because this is a summable sequence. Okay, that's the basic plan. Now, where this comes from, this is basically the energy estimates that I showed briefly yesterday. You always have to, in order to along the iteration to control even the L2 norm, you need to know higher order norms of the previous one. And that's something you already see here on this formula. In order to control the L2 norm of rho q plus 1, I need to know the H1 norm of rho q. Okay, so if I want to do this many, many times, I need to control lots of derivatives. Okay, we don't need it for all n. We don't need it for all n. But why? Okay, I will come back to it. So there's, you mollify, okay?
That's the initial data.
Right. Yeah. It will come. For the moment, yeah, we don't need it for all n, because at some moment we mollify. But yeah, just give me a second. Okay, and in addition, of course, we also have the difference of the L2 norms. So supremum in time, rho q plus 1 minus rho q in L2 is also bounded by lambda q to the minus gamma times dq square root. Okay. And now, so okay, even, well, whether I need it for all n or not, but I need it definitely for a lot of n. But the result I stated in the beginning was for initial data, which is just H1. So I definitely need to mollify there. And so this is, okay. So let me first talk about the main theorem, and then in the meantime, think about your question, which is a good question. The proof of the main theorem. So in the setting of the main theorem, we are given an initial data which is in H1. So we will need to mollify this. But before we do that, what we need to figure out is so this one, okay, this is an estimate that relates the dissipation rate and this lambda q to the initial data. So I can kind of hope that, this part depends on q, this does not. In some sense, if this is satisfied, then it will be it will continue to be satisfied for later Q. So somehow, this condition, I need to find the first Q where it's satisfied. It may not be Q equals 0, because the lambda 0 is not big enough. But eventually, this is going to infinity very fast. This is not going to decrease that much because of this. So, okay, and that first Q0 is where the inertial range starts. So even if you look at physics literature on anomalous dissipation, they say, okay, there are different regimes on scales. Just like in the Navier-Stokes, the full turbulence case, there is a first interval of length scales where you see kind of non-universal behavior. That's the macroscopic or integral range. Then there is at the other end of the spectrum, very small scales. There's always some viscosity. Here there is some diffusivity. There's a very small scale where this diffusion term or the dissipation term would be dominate. It's a dissipative range. And in between, there is an inertial range where it's expected that this term will have a dominating effect. Okay, and we need to first figure out where this starts. So the first step is the choice of inertial scale, Q inertial, Qi. And so, okay, so what I will just show you now is very quickly how to get this. And this is essentially what I've been saying a few times now. If you take for any Q, this equation is the standard energy estimate, which will give you 1/2 dt of rho Q in L2 norm squared is equal to minus kappa Q gradient L2 squared. And now I use Poincaré to say that this is bigger than minus kappa Q, some constant, times rho Q in L2 squared. And the constant, if you want to play with dimensions, which is always useful, it would be inverse length squared. Okay, so this is sort of like something that is determined by the domain. Okay, so this is just a Poincaré inequality. So that means that so any such equation has dissipation, and the dissipation rate, dq, is then at least, so this is, okay, this is equal to 1/2 the initial data, L2, minus the solution at the final time, L2 squared, which by this relationship can be estimated from below by the exponential, 1 minus the exponential. 1 minus exponential of minus 2 kappa Q L0 to the minus 2 times time, times the L2 norm of the initial data. Okay, so there's always this amount. And so I want to essentially choose Q such that this is bigger than, if I put that lower bound here, I get this, at least for n equals 1. Okay, so the choice of the inertial cell Qi will be such that the gradient of the initial data in L2 is less than or equal to lambda Q times, well, let's put Q plus 1 because it's smaller. I just put smaller Q plus 1. Kappa Q plus 1 is smaller than kappa Q. Now, this amounts to, so this is now fixed. It's a fixed number. In fact, so you see somehow a length scale of given by the initial data. I divide by the L2 norm squared, and then this is something which gives me essentially like the length scale of the initial data, minus 2. And this has to be less than or equal to whatever I have here, which is the lambda q times this exponential, 1 minus x, blah, blah, blah. And now I want qi so that this is true for all q bigger than qi. This expression should be bigger than this given number. And then to get that, you just have to figure out that this is actually a monotone increasing expression in Q, which is not completely obvious because if Q increases, this kappa Q goes to 0. So this term goes to 0, and at the same time, lambda Q goes to infinity. Okay, so you have something going to infinity times something going to 0. You actually have to do a small computation. And that computation just involves putting in this expression for kappa q, and okay. You need to be a bit more precise about what is theta. Okay, so that's the first step. And the second step is to modify the initial data. Second step is to modify the initial data. So it's going to be something, and there's not much room left for what scale one should use. It should be something where L is basically lambda q I to the minus 1. It's basically saying, I don't really care what happened before this scale, on larger scales. But now I reach this scale, this lambda qi, this step of the iteration, and in the continuing construction of the uq, I only have smaller scales. And the same way, I don't care about the larger scale part of the initial data. And how much? Okay. So what did I want to say here? This is just essentially standard estimates. Okay. This is less than up to constant. This qi to the minus 1, the length scale of the initial data, which is here, to the minus 1 times the L2 norm. You see, in principle, I should put the H1 norm, but now I can play with this guy. So it's L2. And higher derivatives, hn plus 1, will be bounded by powers of the lambda qi. So these estimates will then allow me to get this estimate for the modified. Okay, so get that, in fact, for all n. Okay, put n plus 1, well, n. This is less than lambda qi to the n times the minimum of dq plus 1. Let's say tilde for the modified guys, but they are very close to the original ones by the first estimate. Okay. So what then happens is that this initial data satisfies and the Q. So I'm ready to apply this iterative proposition, and I get okay, I don't think I need this. So homogenization, or the proposition, gives me that for all Q bigger than Qi, the dissipation rate is bigger than one, let's say 1/2 times the dissipation rate at step Qi. Okay, that's just coming from fixing constants and so on and using that this is a summable series. Yeah, that is not changing anymore. Yeah, I may have to look into the paper. So far, it's still ticking in my head. Okay, so now, well, I do want to write this down. So more explicitly, this is basically given by, so what is the lower bound on the Qi level? That one is just given by the energy and the Poincaré estimate. So it's this one. And I want to keep this because I want to do something with it in a short while. Times DL2 norm of the initial data. And it doesn't matter if you put tilde or not, because they're close enough. Okay, so this gives a lower bound for all Q bigger than Qi. But then there's some sort of simple comparisons, because in the end, so I can now say something about this equation. But I really want to say something about this equation. Let me put Q and sub U. I want to change the UQ to U without touching this one. Okay? So I'm comparing these two equations by taking the difference and looking at the equation, the energy estimate for the difference. I'm not going to go into the detail of this. The point is that the kappa Q, I mean, so it's you can't always compare these two. It depends on how big this kappa Q is, okay? Because the idea it's sort of what we have to do in some of the steps of the proposition also is to put this difference, this UQ minus U, inside the Laplacian. So write it as curl of ZQ minus Z. Put it inside here, and then we have inside the divergence, here I write this as the divergence form. I have to compare kappa Q times identity with this guy. ZQ minus Z cross. Okay, so this is gradient, and this is gradient. The difference of the two. Let's call tilde. Okay, and so eventually it boils down to comparing some norm of ZQ minus Z to kappa Q. So if kappa Q would be too small, it wouldn't work. It has to be large enough. But the kappa Q we have is somehow precisely tuned that it will be the correct size. Okay. And then in the final step, let's say 5, I'm not writing it, I have to go back to the original initial data. So from this modified to the original initial data, and that's again one of these standard energy stability estimates. You have the same equation, two different initial data, you want to compare the solutions. So after all these steps, the upshot will be basically this. Okay, so I just write it again. So for the final equation, rho kappa u dot grad rho kappa equal kappa q rho kappa q. Okay, so there's u. I have the full vector field. I have some dissipation. The dissipation rate kappa q is bounded below by this expression. Okay, I just write 1 minus the exponential, and then initial data. So it's this term, which is what I called C0. And the C0 is basically something depending on the time t and the qi, the kappa qi. The time dependence looks like it's, if I would just forget about this kappa, it looks like it's linear, right? Because it's 1 minus the exponential. So it looks linear, but this kappa qi is also something that depends on the time. It's here, right? It's the qi, so that this expression is bigger than the something given by the initial data. And it's actually worth to compute how this depends on time. Of course, there's the time here also. There was time t, and the kappa q, it's basically the same exponential expression, same thing inside the exponential, except there is the lambda q additionally here. And if you compute that, well, okay, I mean, it's not that interesting to see the computation. What is interesting is that for small t, it's something like this C0 is going to be the computation again. T to the 2 minus 1 minus 2 divided by 1 minus beta times initial length scale of the initial data to the 2, 1 plus beta over 1 minus beta, and the integral length scale to the minus 4, 1 minus beta, where I'm cheating a little bit because in the whole choice of these parameters, there is a b, which is bigger than 1, and the b should enter, but this just gives small corrections to the exponents. Okay, so the b will just add some things, but if we set b equal 1, this is what you get. So I just want to make a connection a little bit to Mario's lectures to finish in the last section, and this is coming from a paper that Mario referred to by Drivas and Eying. Why, you know, the interesting question here is why this exponent of time? So just to say, if beta is 1/3, which would be the boundary, then this is 2/3, so it's t to the power 3. And in this paper of maybe I don't need this either, of Drivas and Eying, they make a connection between what they call the two-pair dispersion and anomalous dissipation. Mario referred to this in his lecture. I want to give more or less the argument from their paper. So this is, they call this a fluctuation dissipation relation. It also runs under the name of fluctuation dissipation theorem, or FDT or FDR. And it's a well-known concept in statistical mechanics. I guess the first example was Einstein's famous paper on Brownian motion. So the idea is somehow that you have these fluctuations and they act like dissipation. So the starting point is, so I hope I'm doing this correctly. I'm a little bit out of my depth. It's the stochastic representation of the particle motion. So okay, so this is the equation. U dot grad rho equal kappa Laplacian of rho. And thinking of this as a transport equation with diffusion given by Brownian motion, there is a stochastic representation, which I think is usually obtained by the backward E2 equation. S plus square root of 2 kappa dw. Okay, so that's the stochastic differential equation for S less than t. So it's backward. We are running time backward, and put the final state. The particle ends up at point X, and we look at its backward motion. And so applying the Ito formula, with the solution, gives you d of rho of x ds s equals, this is the formula that you saw in Mario's lecture. You have the standard terms coming from differentiation composition rule. This is this time at this point, ds, and then you have the term ts dws, right? Okay. So and if I'm looking at the solution, this is 0. So then I can take the integral. Okay, I put it here in time, and then take the expectation, and that gives me the. So taking the integral in time, I have the final time is given by the point x. The initial time is given by the solution of the SDE. Sorry, initial time, initial data. And then you have the stochastic integral, S dws, right? So, and if you take the expectation, this is already deterministic, but it's equal to the expectation of this random field, scalar random field. Okay? So I think this is all very standard in stochastic theory. Since this is the expectation of this random field, what I have here is basically the random field is equal to its expectation plus this. So that gives me immediately a formula for the variance. It's just a square of this expectation, which is the E2 isometry, I guess. What you said is the E2 isometry. Is 2 kappa times the integral from 0 to t of the expectation of a gradient rho squared. Squared ds. Okay? E2 isometry. And now I can integrate this in x. So this is for a single point x. But if I integrate it for in x, so I consider, let's say, the average. I'm on the torus, but I think this argument works more generally. Dx. Since U is divergence free, these are volume preserving. And then you can, okay, so I have this integral in X here. I can change variables. And then basically it disappears, right? So I just have something deterministic. S. dx/ds. Okay, which is the dissipation rate. So the average in space variance of this stochastic field, whose expectation is the solution, is the dissipation rate. And this is what, in this paper, they call the fluctuation-dissipation relation for this PDE. So in this whole argument, U is deterministic. It's a given vector field. It's not a random vector field. It's deterministic. In fact, you can also take the initial data to be deterministic, or it could be a random field. And now, another sort of simple observation in the paper is that one way to evaluate the variance is to take the expectation, maybe there's a 1/2 of the doubled of the product in the product space. So I take two different copies, independent solutions of the same SDE. Okay, this X1 and the X2 are independent solutions, and take this expectation of the square. And then you just expand out. It's the same computations that you saw in his lectures, and you get that this is the variance. And so in particular, suppose that the initial data is now random, smooth, random, with expectation of differences. So it should be essentially Lipschitz, but also the same bound from below. So the expectation, or the second order structure function, if you want to call it a fancy name, is like x minus y squared. Okay, so that essentially amounts to saying I'm looking at a Lipschitz field, but also it's not that different points are overall in average it looks like an isometry. So then I can take take this initial, this is in initial data. I can take the average in this relationship and apply the expectation in the measure parameterizing the initial data on this side, and basically obtain that so the expectation of these two different independent paths squared is on at least on average. I should put probably average in the initial data is 2 divided by 1 minus beta, okay? Because we have that lower bound here. So in general, this is if you take two independent paths of this SDE, you see this this separation, and this is what in the literature, on the physics literature, people look at the motion of particles in a turbulent flow. And the classical picture there consists of the following argument. Well, first of all, for very, very short times, you expect the particles just to keep their velocity, whatever they had, nearby particles. So the separation will be linear because they have different velocities. For very long times, you expect that there's no correlation at all, so it's just the Brownian motion. The separation will be diffusive, square root of t, and in between there is this regime where you expect t to the power 3 separation, which is something that was observed first time in a turbulent flow in, I think, 1926. I believe this is the first ever quantitative observation on turbulence, before 5/3 spectrum and so on. So, and okay. So there's this remark, which was made to us by Theo, that in fact our lower bound for Euler shows that there is precisely this Richardson law. Okay, so that's it from my side. Thank you for your attention. Yes. Yes, so before this final stochastic part, I was essentially showing you that this quantity, independently of the kappa, is bounded from below by some C0 times the L2 norm squared. And this C0, then I estimated, I gave you a way how we could estimate it. It gave this bound, t to this 2 divided by 1 minus beta. If? Yes. Yeah, at the QI. No. The QI is the number of iterations I need to do in this construction until I'm at a scale where I really see this effect of homogenization. Yeah. Yes. Yeah, that's including that one. This formula here includes the t coming from two places in the C0. One is from the QI and the other one is from, yeah. You're asking what is the relationship of kappa QI in terms of t? Let's see if I can. So what is the, yeah. I made the computation, so I should be able to give you an answer. The kappa, say lambda QI is roughly t to the 1 minus 1 over 2 minus theta. Okay, so what is theta? Theta, if I put, okay, so in the case where b is equal to 1, theta is 1 plus beta. So it's 1 minus beta. That's t. Sorry, given t, that's lambda. Okay, so yeah, no, it's I mean, what certainly makes sense heuristically is that it should be a negative power of t, because this is the time. So if the qi is given by the giving me the length scale, so I need to go to that number of iterations until I see that the dissipation is sufficiently strong on the time 0 to capital T. So if the capital T is very small, I need to do things very fast. Yeah. So yes, so this procedure of homogenization is what is related to, I mean, it's giving you a hold on the forward cascade. Okay, because it's telling you, if I cut off, okay, remember the Hilbert bicycle? If I take some small wheel and try to ignore the smaller ones, then what's coming from the first wheel, the energy, is is eaten up by this this wheel that I picked at a certain rate. So it's the energy is coming from large scales, okay, and it's eating it up in a certain direction because it's given by the Laplacian. It's given by a higher kappa. Okay, so it has a direction. I'm not creating energy. I'm definitely destroying energy with this kappa. So that's a forward cascade. The inverse cascade would be the Maxwell demon riding the bicycle. And that one is convex integration. So because in convex integration, if I fix this wheel in the middle, I see that it's still some force driving it. So there's some fake force driving that wheel that is somehow then also driving the first wheel. Okay, so the energy is actually in convex integration, it's flowing the other way. I would say that's a backward cascade. Yeah. Yeah. Sorry? What I mean by that? I mean like the underlying measure is the product space of, I think it's omega usually, the underlying probability space, and it's omega cross omega, the product measure. You take the average on the product space with respect to the product measure. Yes, it's some underlying probability space for this randomness here. I mean, you could also just say, I take a single deterministic initial data, which has this pointwise bound. I bound from below and above this distance, but this is maybe a little too special. You can't have 2 points with the same density, 2 different points with the same density. Then. So it has to be sort of like a monotone. Here? Ah, yeah. Yes. No. Here I didn't want to put it. So initially, yes, I would have that. So this is bounded by this t cubed, okay? But then I want to use initial data satisfying this, so I get rid of the row initial, and I just have this. And then I guess yeah, yes, like this then. Mm-hmm. Because it's t cubed, it's very small, t is small. If it's a smooth velocity field, yeah, then you don't expect this.
Okay, so let's thank László for this beautiful presentation.